So last time we had begun talking about possible sort of direct, indirect searches where you look directly for the products of dark matter annihilation or decay. And we'd focused on talking about photon or neutrino signals where the particles propagate to us undisturbed, and it defined this J factor and this separation of the particle physics from the astrophysics. So to get this piece, you usually have to use kinematic measurements or some model of the dark matter density to try to estimate how much dark matter is actually there in the region that you're looking at. Now, if, as we talked about a bit last time, if we're working in a regime where these particles, where these photons or neutrinos propagate to us and the spectrum is essentially unchanged from what it is at the origin, then we can just say, okay, let's look at the let's look at the cross section. So we can just say, okay, let's look at the spectrum of observed photons per time per area of our detector. This is usually actually my observable. Most telescopes have at least some energy resolution, so you can tell what particles are coming in at different energies. So in this case, this expression, this number of photons per annihilation just becomes number of photons at a given energy per annihilation. So you take the spectrum of photons per annihilation, which you get from your favorite Monte Carlo code or favorite analytic calculation, and particle physics is separated from the astrophysics, and everything else is just the same if there is no attenuation or redshifting. So this is nice because the spectrum we see is just exactly the spectrum that we compare to particle physics. Now, of course, if there is attenuation or redshifting, you have to be a little bit more careful about this. So let's first just do a simplified example in which there's redshifting, but there is no spatial dependence to worry about. This is the most simple case where you do have redshifting as well. Let's suppose that what I'm trying to measure is just throughout the history of the universe, there has been some use of isotropic cosmological dark matter background. There are halos and clumps of dark matter on top of that, but I could just ask, what's the contribution from the dark matter annihilation that's been happening in the homogeneous part of the dark matter distribution through the whole history of the universe? Okay, so this is just sort of an isotropic background that is always there. It tends to be pretty subdominant compared to other searches, but let's just see how we will work this out. So this is the simplest case with redshifting I know how to do. So the easiest way to think about this is to say, okay, so this means if annihilation has been going on through the history of the universe, then we're sitting in a bath of photons all around us, and I can just ask, what is the number density of that photon or neutrino bath? So instead of phrasing this in terms of a specific detector with a specific area per unit time, I'm going to phrase this in terms of a volume. I mean, these are, of course, completely equivalent if particles are going at the speed of light. If I know this number, then I know that if I put down a detector of a certain area in here, a certain number of particles will cross it per unit time. But this is the quantity I want to compute. Okay, so the reason that I'm going to talk about this is, so this is isotropic. It's the same everywhere in the universe. Okay, so this means that I can just, so this is the number density of photons per energy. And my location, I can pretty safely just say that I'm going to imagine that these photons have not propagated through the universe, and the photon bath at my location is just due to the annihilations in my co-moving patch of the universe overall history. This is just because, you know, I mean, it's going to be true in every co-moving patch that some photons are streaming out and some photons are coming back in, but you know, this is a purely isotropic signal, so this is all going to cancel out. So I can just say that this is the integral over all previous times from the number of photons injected because we know the overall number density of photons per co-moving volume doesn't change. But now, so I need to be a little bit careful here. Like this would, if I was just looking at the total number of photons, then I could just do this. I could just do this calculation, assuming that they don't dissipate. But I also need to take into account that they're going to redshift down. So instead of this being my number of photons at energy E at some late time, I want the number of photons at energy E times 1 plus Z at some earlier time. So I want the photons that will redshift down to the energy that I observe today. And photons here can also mean neutrinos. There's no difference between them for our intents and purposes if we're assuming they're not being absorbed. So, okay. So, okay. So what we know is not the number of photons injected per redshift. We know how to write a number of photons injected per volume and per unit time. So let's put in the spectrum per annihilation. And this is, again, this is going to need to be the spectrum at, this is going to be the spectrum of photons at this is going to be the spectrum of photons at this redshift, at this increased energy, times the rate of annihilation, the sigma v over 2, times the number density of dark matter squared. Now that's per unit time, per unit volume. So we're going to have to do a conversion here from, if we just wanted to write this as an integral over time, that was fine. We want to write it as an integral over z, so we're going to have to change variables from dt to dz. And we're going to have to put in a factor that tells us, well, how big, what was the physical size of this co-moving volume at this early time compared to the present day. Okay, so this, like, so this is going to be like dv z over dv, where this is the physical volume associated with the physical volume at redshift z associated with the co-moving. Okay. So what are the factors that we need to put in here? Okay, so this volume factor, well, okay, let's just check that I get this right, because this is easy to get around. So okay, so at early times, the physical volume associated with a given co-moving volume was smaller, right? The universe has been expanding by a factor of the scale factor cubed. So scale factor A scales like 1 over z. So this factor is going to give us a factor of 1 over 1 plus z cubed. It's pretty easy to get confused about which way up this has to go. I find it's helpful just to go back to basics and think, okay, the universe is expanding. The physical volume of a given co-moving volume is larger at late times, smaller at earlier times. dt by dz, well, this, so we can work out what this is. You can show just from the definition of the Hubble constant that if we look at, say, d by dt log of 1 plus z, that's minus d by dt log a, since a is just proportional to 1 over z. So this is minus a dot over a. So this is minus the Hubble parameter. So this tells us that, this tells us that we can write dt. Okay, so this is 1 over z dz by dt. 1 over 1 plus z dz by dt goes like minus h of z, so we can get dt by dz from that expression. Now, furthermore, yeah, okay. So furthermore, this dm by de prime, with e prime evaluated at e of 1 plus z, this is going to, so we want to take into account all the, I want to say this. Yeah, okay. So this is, right, okay, sorry. This is actually, so there's a dm by de over here. So this actually has to be dm by de. If we want to convert it to dm with respect to de prime, the energy at high redshift, we need to put in a factor that takes into account that the width of the bin is also larger at high redshift. So this is equal to by de, and this factor is just 1 plus z. So putting this all together, what we get is that, okay, so from the, also this is n dark matter at that high redshift z. So putting this all together, from this dn, we get the spectrum evaluated at the redshifted energy, multiplied by this prefactor for the fact that, say, the bin from 1 to 2 eV at redshift 1000 will shift into the bin from 10 to the minus 3 to 2 times 10 to the minus 3 today. So the de prime redshifts by a factor of 1 plus z. We're assuming here that sigma v is redshift independent. Of course, that doesn't have to be true, but it simplifies this calculation. We have a 1 over 1 plus z cubed factor from the volume, and from this dt by dz factor, we have 1 over and the minus sign is just incorporated in the fact that for t I'd be integrating from early times out to late times, and here I'm integrating from z equals 0 back out to infinity, so from late times back to early times. If we say, okay, well, we're looking at the smooth isotropic background here, we made that assumption, then we also know how n scales with the redshift. That n scales like, so it's rho dm today divided by the dark matter mass. So this is the number density of dark matter today, but at earlier times in the universe, the density was higher by a factor of 1 plus z cubed, assuming that we don't go all the way back to freeze out. So what we find is that our weighting factor here for our photon bath just becomes this result. So now things are not quite as simple as they were before. So let's take, we're doing the simplest possible background with redshifting, so let's also consider the simplest possible spectrum. Let's just suppose I injected a delta function of photon energy at early times. Well, then in that case, so let's suppose my fundamental underlying spectrum per annihilation is that I get a photon delta function at the dark matter mass. Okay? I guess really I get two. I have two photons, so put a 2 out the front. So then this tells me that, so I can rewrite this 1 plus z so here, this 1 plus z in the integral, I can rephrase that now as just m chi mdm over the energy of the photons that I'm measuring. Okay, that's so then this, and then I can turn this integral over dz into an integral over e prime, and just use the delta function to perform this integral. So then if I do this 1 plus z cubed factor just becomes a 1 over e cubed factor and I need to know what h of z is. If I'm working at late time, so I'm looking at the epoch where matter and radiation, where matter and dark energy are what dominate, then I can write this in this form. So then I get a spectrum like this. So depending on the, so you see, so what looked like a delta function at the origin, in these circumstances the spectrum of this is up to 4. And there's probably a factor of 2 in here. So what started out as a delta function spectrum at high redshifts, now I'm seeing the effects of energy injection at higher redshifts as well as in the present day, and so my spectrum gets filled in to lower energies. So while I started with just a delta function, I'm going to end up with the spectrum that, well, if I ignored this term in the denominator, if my contribution was really just from the dark energy piece, you know, I'd end up with like a DNDE goes like e⁻³ spectrum, because the annihilation rate is earlier in the early universe where the density is higher. Now, of course, this is not actually a signal that we mostly look for, because if you work out the amplitude of this and compare it to the amplitude from regions with much higher dark matter density in the present day, this contribution is pretty small. I hope this gives you an illustration of how you include redshifting. So if we wanted to include both non-uniformity and redshifting, then you can't use this trick of saying, okay, I'm just going to look at the number of photons produced in my co-moving volume, because that's the same it was produced in any other co-moving volume, and they're just going to get spread out evenly through the universe. Instead, what I have to do is take into account, okay, if I've got a source spanning some angular distance d omega, let's figure out how the photons from that source propagate to us, taking redshifting into account. So in general, if we have both redshift and spatial dependence, then we get, then again, now I'm going to go back again asking, okay, how many photons would I see per area, per time, from a given source, and per E. Then what I'm going to see what I'm going to see is just the same result, this same weighting factor of 1 over h of z times 1 plus z cubed, which is basically just coming from, so as we said, the h of z factor is basically coming from the relationship between time and redshift. The 1 plus z cubed factor is basically just coming from the fact that photons or neutrinos produced by dark matter annihilation at early times are going to get diluted by the expansion of the universe, just like anything else. And this piece is just representing the fact that you want to look at the spectrum of higher energy particles being produced, so they'll redshift down to your level. So if we wanted to additionally include absorption, then we would want to put in a factor here of the form you just want to include a term that says, all right, particles produced at some redshift with energy E and in a given direction on the sky are attenuated by a certain amount on their way to us. So in this case, you can still separate some of the particle physics from the astrophysics. You can pull this sigma v over m chi squared factor out the front if sigma v isn't explicitly redshift dependent, but it's no longer possible to disentangle disentangle the spectrum. This spectrum as it enters into this is going to be intrinsically a function of redshift. Okay, yeah?
Could you test for weird cosmologies with this?
So like if you did see a dark matter signal and it had a funny, and you were pretty sure like from other tests that this was a delta function spectrum, but then it didn't look like 1 plus z cubed, it looked like, it looked like some weird evolution. Yeah, I guess so. I mean, my suspicion is that sufficiently weird cosmologies would have other effects, because I mean, you can just look for, I mean, that's not unique to dark matter annihilation, right? Like anything that makes a spectral line, you could do this. So if you were looking at like 21 centimeter lines from the early universe or something, then you know that's a spectral line. So if you saw a very funny energy dependence in the present day, then I'm guessing you would see it there before you would see it, since we haven't seen a signal from dark matter annihilation yet, and this is pretty small. But yeah, I mean, I guess in principle, if you know something is a line or you know something has a specific spectrum, then you can use the dependence. If you know that the spectrum you're measuring is actually from that line, then you could use that to try to disentangle it. Of course, the problem will often be you have a bunch of backgrounds, and the way that you identify this as a line signal from early times is, oh, look, I have this characteristic spectral dependence, so that it looks like a redshifted line. But I guess it is true that the dark matter, because the dark matter scales like density squared, and most other lines do not scale, a lot of other lines don't scale like density squared, you would expect for a given line a different redshift dependence for something from dark matter as opposed to something else. So yeah, if you saw something like this, you could potentially do a test this way. But as I said, this signal from the purely isotropic dark matter distribution is pretty small and hard to see, because we live in a giant halo of dark matter where the density, as I said, the local density is more than 5 orders of magnitude higher than the cosmological density. So generally, if we see an isotropic signal, it's mostly going to come from our halo. Okay, any other questions about this? This calculation make sense to everybody? Okay, so the next question that you can ask, okay, so now we know how to go from a spectrum at the source, a spectrum per annihilation that you can predict, per annihilation at an early time that you can predict from particle physics, to a signal that you will see in your detector. So you might then ask, okay, what are the possibilities for this spectrum? And what does that tell us about how we should look for those spectra? Because I mean, at first glance, the possibilities are essentially infinite, right? I mean, we don't know what dark matter is. We have many ideas for what dark matter could be, but we don't really know how it interacts with the standard model. So I mean, in principle, this spectrum could be anything. So you might say, okay, let's just go look at regions where there's a lot of dark matter and look for funny spectra. And you can do that to some degree. But often you want to try to connect this to a particular dark matter model, and it does turn out that many possible models for how dark matter would interact with the standard model, you can classify the possible spectra that you can produce into a fairly small number of categories, and use that to inform the way that you perform these searches, and which searches are best. So often when you see indirect detection constraints and indirect detection results, you'll see them classified in a couple of different ways. So one thing that you'll very often see is experimentalists will set constraints on, they will say, okay, here's a particular two-body standard model final state. Dark matter annihilates or decays into B quarks, or tau leptons, or electrons. So the logic, and then what's the photon signal from that? So the calculation here is basically that if the dark matter couples directly to the standard model, and there are allowed two-body final states, that's the smallest number of particles in the final state that you can generally have that conserves energy and momentum. Adding more particles to the final state will add more powers of the coupling. You'll have you'll have a larger, more complicated phase space factor. So generally, if the dark matter couples to the standard model and two-body final states are allowed, they will usually dominate. Now, there are a bunch of caveats to this. If you're in a dark photon model, like the ones that Neil talked about, then dark matter does not annihilate directly, does not couple directly to the standard model. It annihilates into something else, which subsequently decays to the standard model. So then your minimal standard model final state is usually a four-body state, not a two-body state. So that's one example. If you have a case where the two-body final state is allowed but suppressed, for example, it's p-wave suppressed because the matrix element is momentum dependent, then it's very possible for a three-body final state to actually be the dominant final state. But if you've got tree-level unsuppressed annihilation and two-body final states, that will often be the dominant mechanism. So then you can consider all possible two-body standard model final states. So this can be, you know, this could be direct annihilation to leptons. It could be production of quarks. It could be gauge bosons. And you can ask, all right, if this was the signal, so I guess there's, so in general you're going to have a linear combination of these different signal channels, but, well, in many circumstances there's one channel which has a large fraction of the branching ratio, and even when it's not, if you know how to search for these individually, then generally the strategy that you employ will not change drastically depending on whether the channel is, e.g., 100% electrons and 100% B quarks, or 100% electrons or 100% B quarks, or 50% electrons and 50% B quarks. So for a broad picture, you can just ask, okay, what space of signals do these channels span? So within that, I guess I'll put in gamma gamma, that's an important and U bar. So within this categorization, there are basically three types of final state in terms of their photon, in terms of their signals. Okay. So state one is is that your final state contains a lot of photons with a broad spectrum. So this is generic whenever you produce in this decay anything hadronic or anything that decays into hadrons or tau leptons. Because these are also known as channels that make neutral pions. Neutral pions are the lightest of the lightest mesons. So if you're making quarks by any mechanism, you tend to make lots of pi naughts. The dominant decay of the neutral pion is gamma gamma with more than a 99% branching ratio. So these channels make a lot of photons with a broad spectrum, and where the broad spectrum is set by these decay paths, by the hadronization, and by the spectrum, and somewhat by the pi naught mass scale. So for states like these, generally the best way to look to them is to do photon searches. These states also make charged pions, which go to electrons, positrons, and neutrinos. But as we'll see, and there are constraints on, and there are antiproton limits that are also relevant. Now, because these are continuum photon spectra, they can often easily be mistaken for astrophysical signals. There are lots of ways to make photons out there in the galaxy. So, so that's usually a concern. So generally, the constraints that best combine being, well, this is partly a matter of taste. You can weigh off how much you care about the constraint looking stringent versus actually being believable. But some of the most robust constraints for these channels come from dwarf galaxies. In general, if you're not looking at dwarf galaxies, if you're looking at a region where you expect the backgrounds to actually be significant, then you have two options. Option one is to try to put in some model for the astrophysical backgrounds and fit for a dark matter signal on top of that. This can often give you very strong limits, but it's subject to the uncertainties in the backgrounds that you are subtracting or fitting out. So there's an unavoidable systematic associated with that. The other thing to do, which is very conservative but tends to give constraints that are somewhat weaker than the dwarfs over most of parameter space, and you'll see this explicitly later, is just to say, okay, we're just going to require that this predicted photon signal not overproduce the actual total number of photons that we observed. Just forget about the backgrounds. So that's very robust. So when you see constraints, say like constraints from the galactic center or constraints from galaxy clusters, should be a couple of questions that you ask. One is, how did they model the J factor? What did they assume about the density? So we talked about this earlier. What did they assume about the density profile of the object? What did they assume about how much substructure it has? And the other question is, how did they model the backgrounds? Did they just ignore the backgrounds, just require that this not overproduce the signal, in which case it's a very robust constraint? Or did they try to do some modeling, in which case you want to think more carefully about whether you consider that to be robust. Okay. So that's the first kind of state. The second kind of final state, broadly defined, is leptonic final states. So you can pretend, so this is electrons and positrons, or muons and anti-muons. Muons decay to produce electrons and positrons and neutrinos and antineutrinos. So in this case, the photon signals are rather suppressed. Well, there are two types of photon signals in states like this. One is from three-body final states. So you have, if you have an E plus E minus final state, you can always radiate a photon off the final state, but these are suppressed by alpha. Generally, there are also contributions to the photon signals from the electrons and positrons upscattering ambient photons, or propagating magnetic fields and producing photons after they're produced. So however, so these signals can potentially be very large. Just because you don't make any photons directly doesn't mean that you don't make photons, but this requires modeling of the electron and positron propagation. So these models models where these are the dominant final states, which can happen naturally in dark photon models where the photon is too light to decay to anything else in the standard model. People also write down models that are explicitly leptophilic, although that can sometimes be, in that case you can have cases where, as well as these final states, if the dark matter is sufficiently heavy, you can have electroweak Bremsstrahlung, so you can produce W's and Z bosons in the final state, just because the electron and muon interact weakly, and W's and Z's have decays to quarks, and so then they can get you back into this regime where you make a lot of photons. So these are typically best constrained by cosmic ray experiments, by searches for the electrons. And also by constraints from the early universe, where you just care about the injected power. And if there's no experiment that can see the electrons in this energy range, sometimes by the subdominant photon signals. But one of the things that happened about a decade ago was that people started taking models like this much more seriously, and it really does change your intuition for which signals are likely to be most prominent. Dwarf galaxies don't tend to do very well at constraining signals like this because, well, dwarf galaxies are too far away for the electrons and positrons to get to us. You can look for the photons, but this channel is suppressed, and dwarf galaxies don't have a lot of starlight or high magnetic fields in them. So as a result, the electrons and positrons tend to not lose very much energy in dwarfs. So the third broad category, I guess there are really 4 categories, with the fourth one being everything goes 100% into neutrinos. But that's pretty simple to explain how to look for it. You need an experiment that detects neutrinos. So category 3 is you're looking for sharp signals, lines or sharp features. So these searches are a bit different from the other searches here. They're much less subject to worries about astrophysical backgrounds because you can look for spectral information. So in these cases, what you generally do is perform a bump hunt. At X-ray and at gamma ray energies, there are essentially no backgrounds. At X-ray energies, you do have to worry about backgrounds from atomic lines. But if you had a signature like this, it would allow you to avoid a huge amount of worry in terms of, oh, is this continuum signal that I'm seeing actually coming from some astrophysics, or could it actually be coming from dark matter? So when I said lines or sharp features, this can also include cases like the FSR, like the final state radiation that I mentioned over here. This final state E plus E minus gamma gives rise to a pretty hard photon spectrum. So you can sometimes look for spectra like that in the same way that you could look for a line. If there are degeneracies in the spectrum, you can get narrow box diagrams or sharp peaks. So these can also fall into this category. The thing is that for these line signals, the predicted rate tends to be very small, at least for photons. We know that dark matter is not charged. That means that the gamma-gamma signal inevitably has to be loop level. So this means the backgrounds for this are low, the rates are typically very small, everything depends on statistics. So often for these signals, you want to search at the galactic center because that's where the backgrounds there are pretty challenging, but if we're lucky and the dark matter density rises there, the event rate could potentially be very high. Likewise, you can look in clusters for these lions. We don't know how much dark matter substructure there is. If there's a lot of it, the event rate could potentially be very high. And yeah, so option 4 is nature is not friendly to all of us, those of us doing photon searches for dark matter, and your dark matter, for whatever reason, annihilates odd k's to neutrinos. If your dark matter is sufficiently heavy, you can still get a photon signal. Via production, via electroweak Bremsstrahlung, essentially. You can produce 3+ body final state with Z's or W's, so you can radiate off W's and Z's like BREM, but this requires your center of mass energy to be pretty large compared to the W or Z mass. So this only really matters for dark matter, usually well above the TeV scale. If that's not the case, your hope is to look with neutrino telescopes. Now, for most other channels, the neutrino telescopes do not do as well as photon telescopes, just because neutrinos are vastly harder to measure than photons. There are some exceptions at very, very high energies. The constraints on neutrinos can be better than those from photons, even at even for channels that are not pure neutrinos, just because this is partly a matter of experimental reach. It's partly a matter of high energy neutrinos don't get attenuated. Sufficiently high energy photons do get attenuated if they're coming from outside our galaxy. But yeah, so I'll show you some explicit results later. But mostly neutrino telescopes only dominate the constraints if you have a large branching ratio straight into neutrinos, because it's hard to find any other way. Okay. So we've talked a fair bit about, so now that we've talked about these different kinds of spectra, well, I've talked about the photon signals, I've talked about how to compute the J factors of those, how to include the effect of redshifting, but I've told you that at least for this significant chunk of signals, you don't have a lot of photons, you do have a lot of cosmic rays. So the question will be, okay, how do we understand signals from cosmic rays? Also, even for the photon signals, so the dominant way that gamma rays are produced in our galaxy is by cosmic rays interacting with the interstellar medium. Not cosmic rays from dark matter annihilation, just ordinary cosmic rays accelerated in supernovae. So both for understanding backgrounds and signals, modeling the propagation of cosmic rays can be pretty critical. So when I talk about this background process, what I mean is if a high energy cosmic ray interacts with the gas, it's a high energy proton scattering off another proton, just as hadronic channels of dark matter annihilation produce neutral pions, which produce gamma rays. When a high energy proton runs into an at-rest proton, in general pions will be produced, which make photons. So this is actually the dominant background at gamma ray energies. So it's important for the background and for the signal, especially from leptonic channels. Okay, so what I'm going to do here is just try to give you a very quick overview of how you do modeling of cosmic ray physics. Now, this is not something that you would actually use to do a calculation. This is going to be back of the envelope stuff. The way that this is actually done in practice is to use public codes. So, is to use public numerical codes, of which two of the popular ones are called GalProp and Dragon. So the challenge here is that, well, there are a couple of challenges. One, we don't know exactly how the background cosmic rays are produced. We think they come from supernova remnants, but we don't know in detail, say, their spectrum of production or exactly where in the galaxy that we're being produced. This is something that we try to fit from data. So, second, the reason why cosmic rays are challenging to model is that they don't travel in straight lines. The galaxy is pervaded by a magnetic field. These are charged particles. So the way that cosmic ray propagation in the galaxy is typically modeled is as diffusive propagation. So let's write, okay, so this is the back of the envelope approach to diffusive propagation. Let's write, the quantity I'm going to be interested in is the number density of cosmic rays of a given species as a function of energy. Okay, so this is number density. I want to know throughout our galaxy, how many CRs do I measure? So if I have, so there are experiments like AMSO2 in orbit around the Earth, which measure the local cosmic ray flux. So this is a prediction for those experiments. So I'm going to call this quantity SAR observable. I'm going to call it psi as a shorthand. Now the diffusion equation, which in most of these models phi is assumed to obey, has the following form. Okay. So this is not back of the envelope, by the way. This is the actual equation that these codes attempt to solve. Will become back of the envelope very shortly. So this term describes diffusion, where d of e is this energy-dependent diffusion coefficient. Now in reality, this diffusion coefficient probably depends on position as well as energy. But in the standard simplest approximation, it's assumed to be purely a function of energy, same everywhere in the galaxy, and the same for diffusion in all directions. Both of those assumptions are probably wrong at some level. And so there have been various attempts to include anisotropic diffusion or spatially varying diffusion. But the baseline, even in these public codes, is still just this prescription. This term describes energy losses. So B of E here is this energy loss coefficient again. We're assuming this is only a function of energy, not a function of the rate of energy losses within the galaxy. And then this term here is describing the sources of cosmic rays. Now you can add other terms to this equation. You can both try to make these diffusion and energy losses anisotropic or inhomogeneous, or you can add things like convection of the cosmic rays, so it's not just diffusive transport, but convection or winds can take the cosmic rays out of the disk. So like this would be a vertical convective effect, moving the cosmic rays out of the plane. You could include something to include a term that's called diffusive reacceleration. So the cosmic rays, after being produced, can be reaccelerated, even as they're diffusing. This gives you a term that is like diffusion in momentum space. Or you could say, okay, we're going to allow the cosmic rays to decay or fragment away, obviously. Say we're dealing with unstable species, we'd need to include that. Some of the cosmic rays can include radioactive nuclei, in which case you have to include this term as well. So then we just include a decay term in this equation. But for purposes, yeah?
And how do you achieve convection for this cosmic rays? Is it some kind of scattering?
So it's normally thought of as you've got a galactic wind or something similar that is helping to transport cosmic rays out of the disk. We don't know to what degree these things exist. I mean, there's some evidence from like winds out of the galactic center. There's you can measure evidence for like high velocity transport of particles and gas out of the galactic center region. How pervasive that is, or how common it is still fairly unknown at this point. But these models with convection give better fits to some observations. Yeah, the science of modeling cosmic ray propagation in the galaxy is still, as I hope you'll take from this, I mean, it's very challenging because the observables that we have to measure, we can measure cosmic rays in our local neighborhood. Until recently, that's meant inside the solar system. So the cosmic rays that we see are actually also affected by the magnetic field of the sun, by the solar wind. So we've basically got one measurement point, and we're trying to deduce from that what cosmic rays are doing throughout the entire galaxy. So it's challenging, and this is one of the big challenges for dark matter indirect detection when you're looking for continuum signals. I mean, I believe you can get around it, and I'll tell you some reasons why, but it's that the background is more or less density of cosmic rays times distribution of gas in the galaxy, plus terms from cosmic rays interacting with the starlight, and we don't know the 3D distribution of gas in the, I mean, we have information on it, but we don't know it well enough that these systematics are dominated by statistical errors to figure out the 3D distribution of gas in the galaxy, the 3D distribution of the spectrum of cosmic rays in the galaxy, or the 3D distribution of starlight in the galaxy. and your background is a linear combination of products of these things. So that's why there are large systematic errors. It's not like anyone is doing anything wrong or stupid. It's just there's not a lot of information to inform these models.
How well do we know the magnetic field?
That's another thing that we also don't know very well. So, I mean, you can make measurements of the magnetic field in a couple of different, so like for example, you can look for synchrotron signals from electrons losing their energy in magnetic fields. This gives you sort of a joint constraint on the electron distribution in the magnetic field distribution. Neither of which we know, but it's a joint constraint. You can also do things like looking at Faraday rotation of light from pulsars. As the light comes to us as polarization can get rotated by the magnetic field. So in general, the picture is that the magnetic field in our region of the galaxy is of order a few microgauss, and towards the galactic center it may be substantially higher than that. Like there's some evidence for milligauss fields in the galactic center. But if in the region of say 100 parsecs around the galactic center, you could say, okay, I'm going to guess the B field is about 10 microgauss, and people would say, yeah, okay, that seems reasonable. Or you could say 50 microgauss, and people would say, oh, yeah, that seems possible. So it's again not very well known. So this is another complicating factor when looking at these leptonic channels, looking for the inverse Compton scatter, looking for the signals from electrons produced by dark matter annihilation scattering on photons or scattering in magnetic fields to produce synchrotron, is that we don't really know the B fields very well. What you'll typically do for synchrotron constraints is say, okay, here is my constraint as a function of the magnetic field that is present there. But yeah, there's a reason that we like photon signals better, and that everyone hopes for a gamma ray line, and then we wouldn't have to worry about all this stuff. That said, as you'll see there, as I'll show you, there are some ways to distinguish between possible dark matter signals and just astrophysical signals. But okay, so just starting from this diffusion equation, we need to do one other thing for this diffusion equation. We need to impose boundary conditions. So the typical boundary condition that is imposed is to treat the galaxy as just a cylindrical slab with cylindrical symmetry. Okay, and typically this radius r will be, sort of order a few tens of kiloparsecs for a Milky Way sized object, and the height will be order of a few kiloparsecs. Again, just for scale, the Earth is about 8.5 kiloparsecs from the center, of our galaxy. And normally you say that at the boundaries, there's free escape. So at the boundaries, the cosmic rays just free stream outwards. So then you largely have the cosmic rays confined to this halo within the galaxy in a cylindrical slab, within which they diffuse and lose energy as they propagate. So, okay, now is where, and the other approximation that's usually made is that the diffusion coefficient is just parameterized as a power law. Okay. Now, there are some, so the details of this power law basically depend on the degree of turbulence in the magnetic field. There are some theoretical models for what delta could be. So, for example, two theoretical models of the turbulence, which are called Kolmogorov and Kregnin diffusion, predict delta equals 1/3 or 1/2, respectively. There were earlier studies, people often talk about delta of about 0.7 because that seemed to fit earlier cosmic ray studies better, but the more recent papers seem to be finding something closer to 0.4 to 0.5. Okay. So far, this is not the back of the envelope bit. That was the, this is standard approximations that are made in attempting to calculate these cosmic rays. Now we're going to do the back of the envelope bit. Okay. So, a way to, okay. So let's look at the steady state solution to this problem. We think our galaxy is approximately a steady state cosmic ray wise. It's been around for a long time. So in that case, let's just set the left hand side of this diffusion equation to 0. Now, okay, this is still a kind of annoying differential equation that we would need to solve. So let's just try to figure out sort of the order of magnitude of these terms. So let's characterize the diffusion and energy loss processes by timescales so that we can write so our goal is to write this steady state equation approximately as there's a rate at which the phis at a given energy, at which the number density of a given energy is depleted due to diffusion. There's a rate at which it's depleted due to losses, and then it's being sourced by, this source term. So in the steady state, we want these to balance. So what are these approximate timescales? Well, so this is a grad squared. So this says units of 1 over length squared. The length scale in the problem is the distance to the boundaries, r or h. So I'm going to take this tau diff to be r squared over d of v. Could be h squared too. The difference between h and r is immaterial at the level of the approximation that we're making. Okay, so just saying this is the length scale in the problem, so this goes like d of e over r squared. Okay. Tau loss. We're going to so again we're gonna look at this. So if this is a power law, then the derivative with respect to e will just be 1 over e times the power law times the coefficient. So that approximation was true. My timescale for energy loss is going to go like e divided by this coefficient b of e. This is the very hand-wavy way to solve differential equations. So we can then say, okay, we can identify two regimes here. So the steady state solution is going to be a balance between these changes due to diffusion and losses and the source term. We can identify two regimes. So there's a case where we're diffusion dominated, where the fastest time scale is the one associated with diffusion. And we can identify a regime where we're loss dominated. So in the diffusion, in this diffusion dominated regime, we'll drop this 1 over tau loss term, and our solution is just going to be phi goes like q tau diff. So tau diff we said was r squared over d of e. So in particular, by this parameterization here, our energy dependence is going to be like e to the minus delta times whatever the energy dependence of the source is. So the effect of diffusion is to soften the cosmic ray spectrum by an index delta. So this is the appropriate regime for protons and antiprotons, which lose energy pretty slowly. So most of the galaxies, their regime is diffusion dominated. Okay, so what happens in the other case where we're in the loss dominated regime? So in the loss dominated regime, okay, to do this we need to say something about what the energy dependence of B of E is. So the loss dominated regime is most relevant for electrons and positrons because they actually lose their energy pretty fast in our galaxy. So light processes, and the main loss processes a synchrotron. So this is E plus, E minus, E plus or E minus spiral in a magnetic field. They radiate photons. And what we call inverse Compton scattering, which is just like Compton scattering, an electron hits a photon, except in this case it's usually the electron that's very high energy and the photon that's low energy, which is the opposite situation, the one you would usually encounter in the lab. So this is like E minus gamma goes to E minus gamma. But the photon picks up a lot of the electron's energy on the way out. Now, both of these, over most of the energy range, scale as B of E as proportional to E squared, and which you can just check for yourself from QED if you want to. So this tells me that tau loss here scales roughly like e to the minus 1. So higher energy particles lose their energy more efficiently and they travel for a shorter distance. So this tells me that phi in this regime is going to go like Q times tau loss. So this is going to scale like Q of E times e to the minus 1. So this is a softer spectrum than the e to the minus delta spectrum. So we also see that tau loss gets smaller, so losses get increasingly important at high energies. So if you're in a situation where you transition from the diffusion, the diffusion will be more important at low energies, the loss is more important at high energies, is usually the picture. So the sort of generic behavior is that you'll have a spectrum that at low energies you may expect diffusion to dominate, and then it breaks to a softer spectrum at high energies once losses dominate over diffusion. So if we have a power law, a roughly power law-like injection spectrum, then the expected behavior is that the output cosmic ray spectrum looks like a broken power law. Now this Q of E, this could be cosmic rays directly accelerated in supernovae, but it could also be other cosmic rays hitting the gas and producing the cosmic rays that you're interested in. So we call the former primary cosmic rays and the latter secondary. For example, when a proton hits the gas and makes neutral pions which make photons, it also makes charged pions which can make positrons. So if we see that basically from this, we expect diffusion and losses to soften the spectrum of secondaries relative to the spectrum of primaries by an amount that is by an index which is between delta and 1, depending on what regime they're in. So generically, secondaries should have a somewhat softer spectrum, somewhat fewer particles at high energies. When you see exceptions to that, it usually means that it's usually a signal that there's some source population of cosmic rays that you're not, some primary source population of those cosmic rays that you're not taking into account. And as we said before, so this is not minus, this is delta 2.1. As we said before, the current experimental constraints seem to suggest delta of about 0.4 to 0.5. Now, okay, these estimates that I've done so far are fine if Q of E is a power law. They become a pretty bad approximation of Q of E if the source is very, very non-power law-like. So imagine that we had dark matter annihilation that was producing, like dark matter goes to E plus E minus. In that case, the electron and the positron will just have energies at the dark matter mass. It's a very non-power law-like distribution, and so you might think, okay, that may give me a nice spectral feature that I can look for, just like I look for photon lines. But let's just do this case. Let's imagine that we're in a steady state loss-limited regime. And our source is a delta function, or it's proportional to a delta function at the dark matter mass. So then our diffusion equation becomes some prefactor times a delta function. So if I know that the derivative of this object with respect to energy gives me a delta function, that tells me that this B of E times psi is a step function. And since I know that B of E scales like E squared for the main processes, this tells me Q naught here is just a proportionality factor. So just as in the redshifting case, where the effect of redshifting was to take an initial delta function spectrum and spread it out to much lower energies, the same thing happens here. we get a spectrum that is falling, like ETA. So from a delta function injection of electrons, about the sharpest spectrum that you could have, what we expect to see instead is a spectrum for DND that is falling, like e to the -2, before it cuts off at some mass scale. So even delta function injections give rise to power law spectra under diffusion and losses. So in this case, the diagnostic of initial delta function injection may be that there's a hard spectrum and there's an endpoint. Yeah. Okay, so what you would do to try to distinguish this dark matter signal from an astrophysical signal is to look for this hard spectrum and an endpoint, but some astrophysical sources also have cutoffs. Okay, any questions about this? This is basically what I want to tell you about cosmic rays. I mean, it's just so that you have an intuition for roughly how these things work. If you inject a delta function, you get a hard power law with a cutoff. If you inject anything else, then the effect of diffusion and losses is basically to soften the spectrum, but in an energy-dependent way. So most of the backgrounds that you will look at in cosmic rays will look like broken power laws. Yeah.
Do these broken power laws correspond to these knees?
So that's actually a different thing. Yeah. So right. So that's a yeah. When you get up to sufficiently high energies, you don't really see cosmic rays from our galaxy anymore, and so you're looking at an extragalactic population. So that transition from galactic to so there are right. So there are there are various other kinks in the cosmic ray spectrum which can come from some of the assumptions that I have made here. Some of the assumptions that I've made here are breaking down. But, yeah, and in particular, that's galactic to extragalactic transition. Yeah.
Is there something about the angular resolution of such experiments, or is it just able to look for the spectrum of the particles?
Right. So some of these experiments can have quite good angular resolution, but angular resolution does not help you that much because the magnetic fields scramble the arrival directions of these objects. So even if you can tell their arrival direction very well, that doesn't necessarily help you tell where they came from. I mean, it does to some degree. If you could measure anisotropies that were well below the % level, then that would be helpful for distinguishing possible sources. But as I'll show you when we talk about it, there's this excess of high energy positrons in AMS. It's very well established now. It's been seen for years. And it doesn't look like what you'd expect from ordinary diffusion, because we normally think that positrons are secondary particles produced by protons hitting the gas. But the ratio of positrons to electrons is actually rising in this high energy regime. So that looks like the positron spectrum is harder than the electron spectrum, which is not what you would expect if the electrons are primaries and the positrons are secondaries. But so that suggests that there's some new primary source of positrons out there, and the leading explanations for a long time have been, well, maybe this is dark matter or maybe it's pulsars. If it's all coming from one pulsar, like one single pulsar, then the predicted level of anisotropy is below 1%. So yeah, the galactic magnetic fields do a pretty good job of scrambling arrival directions. But yeah, so I'll talk a bit about this later. It is possible that anisotropy can serve as a diagnostic. We just have to do better at measurements of anisotropy than we do at the moment. You might also ask, if you're looking for this endpoint, the energy resolution of both the energy resolution of the instrument and just the statistics that you have are also important, because I mean, it may be, I mean, this cutoff is a very sharp cutoff, right? I mean, this is a spectrum that looks like this, and maybe the astrophysical signal looks like this. So if you could really measure the endpoint accurately, then that's as good as a bump hunt, basically. But it's hard to measure the spectrum accurately due to a combination of the telescopes don't have infinite energy resolution, and well, in the case of AMS, the statistics up at this high point, I mean, Pamela's number of, Pamela, which is the precursor experiment to AMS, and their highest data point, I think their signal was based on 12 positrons. So yes, there is a statistical limitation. Okay. You know, I mean, we could keep going. So, okay, so that's what I wanted to tell you about cosmic rays. That's basically all the background that I wanted to give you to understand the, this should mostly be enough background to understand indirect detection searches that are presented to you and to understand what we're going to talk about next. We talk about the various signals and their backgrounds. So, you know, I mean, I could spend 15 minutes now showing you pictures. I mean, we started a bit late, so I mean, I could spend 15 minutes now showing you pictures, but it will probably take us a few minutes to set up the laptop anyway. So I think we might just go have lunch now, and I'll begin tomorrow's lecture showing you the current constraints, and then we'll talk a bit more about the anomalies, the present anomalies in indirect detection, and yeah, about the anomalies in indirect detection, and focus in on a couple of them.